theme for an extra conference, or
we can think about organize a seminar, a webinar, a workshop, or something like this specific on the topic. Okay.
Very good.
Yeah, I think that we have now to introduce the next speaker, which is Josué Sznitman. Welcome. Josué Sznitman is associate professor with tenure at the Department of Biomedical Engineering at the Technion Israel Institute of Technology. He's currently an associate editor of the Journal of Biomechanics and Clinical Biomechanics. Among his accolades, Sznitman was awarded the Young Investigator Award in 2015 by the International Society of Aerosol in Medicine for a researcher under 40, and most recently the 2018 Emerging Scientist Award in Drug Delivery to the Lungs by the Aerosol Society in UK. So I am extremely happy to introduce a young, brilliant researcher. So Josué, the floor is yours, please.
Thank you.
Hi, Josie. We look forward.
Hi, Klaus Michael. Let's see. I'm going to put this up. There you go. And I need to duplicate one short moment, please. Display settings. Duplicate. Is it visible now?
It's the wrong mode. Now it's perfect.
Okay, here we go. So first of all, thank you, Samuel. Thank you to all the teams. It's an absolute pleasure, although virtually, to see so many of my dearest colleagues here. Klaus Michael has been an inspiration. I'm a huge fan of Otmar Schmid, and he knows that. And I'm looking forward to some of the other talks, including colleagues from the United States. I'm going to put for a moment the focus on inhalation assays, and this bridges, I think, quite nicely with some of Otmar Schmid's review in the first part, and also touching upon the story relating to dose delivery. So you're going to have a very engineering focused kind of talk here. I'm going to unapologetically take an opportunity to share with you a special issue that Klaus Michael and I and Leslie Yao in Australia put together on indeed what we're talking about today, which are innovative in vitro models for pulmonary health and disease. I'm quite impressed and slightly honored and surprised that we've hit over 50,000 views on this special issue. So given the niche focus, I think it shows that it's definitely an attractive topic, and I welcome anybody to check it out. So let's kick this off. I enjoy very much using this slide for a single purpose, is kind of my engineer's eyes in treating the problem. By all means, one of the reasons why I ended up doing my career in this field, in the respiratory arena, has to do with this, what I call in the title, the multi-scale challenge. And by that, I mean that obviously the organ is so complex and it just sweeps through so many orders of magnitudes of just sheer size. Put aside for a moment the complexity of the morphology, the anatomy, just put aside, but the fact that you need to construct or think of a system that spans so many length scales and such a vast surface area already puts from the starting point one of the challenges that will be needed to be addressed, if not faced, when diving into the world of in vitro models. And in a minute, it made me smile because Klaus Michael used one of his famous phrases, and I'm not going to give it away. It'll come in a moment because I just heard my record playing. To show you, and really, there's the take-home message here is please don't get bogged down by all the little details. I wanted to share with you that whether you're going in vitro, in silico, or the bridge of both, there's always going to be a price to pay. I strongly adhere to the motto that there is no free lunch. And in this world, when you address something like a multi-scale system, the state of the art, however good the computational fluid particle dynamic models are, they are based nevertheless on models. Now, these models are based on the airway geometry, which you can see in the left pillar, the flow modeling in itself, what kind of techniques you're going to try to use in addressing that, and of course, what is flowing through the air, which is of course the airborne particles. So there's always something that needs to be checked in the backbone of the model. On the right-hand side, what I just wanted to show you briefly is that this no free lunch rule of the multi-scale challenge means that by and large, I think it's fair to say there is no single group on planet Earth, to the best of my knowledge, that is capable of giving you a straightforward from mouth to deep lung deposition that is real, that is not based at some point on some articulation of a model of a lumped representation of such. We do not have a full scale resolution because of the computational costs, because of the realism in the models that we have, because of the imaging limitations that at some point we are faced with when trying to reconstruct various lung morphologies. So what you're seeing in the picture is that by and large, you have basically cut-offs or segments of what we do with some confidence and try to bridge these. I'll give an example from our group just to show you that when we address acinar airways, so the deep lungs, right, the respiratory regions, you live in a world where there is no human-based imaging data, and I'll be happy if somebody corrects me. There is no open source kind of human image-based data. For instance, like in the CT world, if you had to do a lung CT, typically they're upper and mid bronchi and extrathoracic airways, of course, but the acinar region is so complex and so minutely small that it's not an option. So models such as the ones we've driven are based on statistical representations that are founded, but they remain models. But with that, the world of CFD gives you an option of having fully resolved and time resolved models of the physics of aerosols. And you're welcome to have a look at this. Here you really see 3D spatially filling acinar structures that are full trees that exist with alveolar cavities and so on and so forth. Why do I bother you with this? For the simple reason is that the minute now your mind is going to go back to the in vitro, then you see that there's a giant discrepancy. And amongst other, Otmar alluded to this, that how do you do this translation between however sophisticated your in vitro model is? So of course you can back out all sorts of deposition data, and we don't need to delve into that for the time being. It's about what can be done and how realistic it is, in particular when you're seeking in vitro and silico correlations. And so now is the punchline that I guess I'm just paraphrasing Klaus Michael, but I'm using a famous quote from a statistician in that all models are wrong, but some are useful. As long as you abide by this rule and you know that before you're heading full forward and you don't want to go into a wall, you need to accept that however good our in vitro model is going to be, it will at best be in a strong position to address some very specifically articulated questions. And that's one of the trade-offs that we live by in this in vitro. And the crowd here obviously knows this, but you know, when you train scientists to address this, it's an a priori process, right? You need to do this uphill so you don't completely overwhelm yourself with the complexity of the in situ system. We've gone broadly over this. What are the kind of preclinical in vitro gold standards in our field? Yes, we went from the world of liquid-liquid interfaces to the world of air-liquid interfaces. Both Klaus Michael and Otmar have really given a wonderful overview of that. So I don't think there's so much a need to repeat that. I'm going to give you the edge of what's the new generations, which Laura has really put an emphasis, and Klaus Michael showed you some examples from our group, which I'll iterate. The point I want to bring up, and it's in the bottom right box, is the limitations. I'll use a different word. It's really the opportunity to address some of the limitations. And again, seen from this engineer's viewpoint, there's an issue that whether it's an LLI or ALI, we're still faced with issues that are relative to the in situ world, scale, anatomy, flow physiology, being respiratory airflows, and of course, aerosol exposure, which lives, so to speak, within the airflow physiology. So I was invited, actually, I guess Klaus Michael knows that he was having a birthday, so it's no surprise, but a number of papers will be coming out in the near future in his honor. And I had a chance to contribute one of such pieces with my group. And I think it's fair to say that today, when one thinks of advanced in vitro pulmonary platforms, I'll make the case, it's not a strong case, I'll call it a working definition or a school of thought, that as I see the field at the moment going beyond ALI, there are two schools of thoughts or two schools of engineering approaches. The first category that you see on the top left has to do with the world of flexible membranes. Typically, these look and have a flavor of having arrays like an transwells, right? But with now the option of having rather sophisticated moving boundaries, moving membranes on which you will regrow an alveolar capillary barrier, as complex as it might end up to be. And this is precisely what you're seeing here, freshly off the bat, came out of the oven this year, a wonderful example of this alveolar epithelium on these flexible membranes with a confocal microscopy with staining, say, of the nuclei. And you see these breathing membranes. But in your mind, you need to consider this as being kind of arrays for medium to hopefully high throughput kind of assays. The second family, which is, I guess, where I reside, for better or worse, it has to do with the world of the microfluidics. And here I'd like to make the point, or at least advance the fact that in the microfluidics, and again, everything I say here is always with a grain of salt, because any category we pick will always abide by the no free lunch rule. So in some sense, the microfluidics, unlike the flexible membranes on an array, have the options to give you some extra versatility and opportunity to go more in the anatomical realism, shall I say, and morphological and flow-based realism. It's not a perfect score, and it will never intend to be. And that needs to be realized very soon and quickly. In general, the kind of approaches that stem from my lab, if you look at the scales, and again, it goes back to this multi-scale challenge problem, is that we've, in the past few years, really kind of self-sufficed in the sense that we've done as much in-house work as we could. And 3D printing has brought us a very, very long way. It's fair to say that these days we use our own 3D printers to create structures that generally cross over in what would be in the lung, something like terminal to respiratory bronchioles. That's kind of the cutoff where you hit the millimeter, maybe if you push through half a millimeter. Once you go into really the acinar world, you need to rely on more quote unquote traditional manufacturing techniques. They're advanced techniques, but they're photolithography, dry or just ion etching techniques, and so on and so forth. Because again, the features, and I'll show some of these, are something like 100 microns, 50 microns, 20 microns, and at least within my budget, I certainly don't have any 3D printers. Today, I'm going to just showcase the work that pertained to what I call the bronchial acinar airways. We've worked on the mid-bronchi, in particular, at looking at therapeutic opportunities for what is relating to the biotrauma incidence. So how, for instance, ventilatory flows during invasive ventilation can lead to the onset of inflammation in 3D reconstructed bronchial epithelium. But this will be, I hope, when I'll have a different opportunity to talk about this. Okay, so just so everybody's on the same page, as gorgeous and beautiful as I'd like to hope that these kind of chips are, we need to keep a time frame. It's very important that the physical aspect is really the low cost at all levels, certainly at the emotional level. When you create these chips, which are in many ways just fancy ALI systems, you know, I don't want to oversell it either. It's important to keep our feet on the ground. They are basically advanced ALI platforms. And these advanced ALI platforms, why do I say that? Because they're based also on the use of these thin PET-like membranes and so on. You create a model in, say, a day or two, which is on the left-hand side, And just like everybody that does cell cultures, you're faced with anything from weeks to about a month if you're using, for instance, primary cells. If we use various cell lines, then of course the time scales are much shorter. And I'll come back to these a miracle, like I like to call them the miracle Hailvi cells, because they're kind of a little bit of best of both worlds, but we'll get back to that in a second. And this needs to be very clear. This is something that bothers me profoundly, and it needs to be recognized because it has a lot to do with how we think of deposition and dose response and dosing and concentration. Microfluidic platforms are three-dimensional in the sense that the flows going through are 3D. There's nothing to say about that. But let us not forget that in nearly everything I've seen, whether it's the flexible membrane world or the microfluidic based systems, we are looking at basically two-dimensional carpet. In essence, it's like saying just one of the walls has a cell culture. And that needs to be recognized because in that sense, it's still very much latching on to a traditional ALI. And that has repercussions when you think of deposition between in situ and in vitro, be it even the in silico simulations that I've shown you in the first part, which are literally real real, or shall I say, physiologically realistic three-dimensional air spaces. This is certainly not. Now, with that caveat in place, you can nevertheless do not just gorgeous, but extremely insightful work. What you're seeing here are dimensions that are basically at the crossover about 1 millimeter. So they're bronchiole-like structures. And you see kind of, it's a chip that in your hands, you see the airways. That's what you're seeing on the left-hand side. So we've grown a normal human bronchial epithelial cells on these. And we've characterized that they are functional barriers in the sense that we have differentiated cells, including the secretory cells. What you're seeing in B and C are respectively scanning electron microscopy and staining of the mucus. So you see mucus structures on the left and blue staining of the mucus on the apical side of the chip. D gives you a sense that you can really get a full carpet across a rather large area. These are big chips. I mean, you would basically see the epithelium, or I mean, the macro view of the epithelium. And in E, you see a blow up with F-actin and nuclei. And very importantly, of course, because we're looking at deposition studies, is of course the barrier properties. I'm not showing here per se, but we discussed that. Klaus Michael has discussed everything pertaining to things like TEER, transepithelial electrical resistance, which is of course super important. I don't need to highlight that. Not to mention also permeability assays, which we do, but I wanted to highlight the fact that it's important to have the tight junction complexes here, for instance, Z01. Okay, so I come back for a moment to the physical side. Okay, so you can create a biological environment, a pseudo 3D, let's just be honest between ourselves, a 2D, large scale, a bronchial epithelial system that, yes, indeed can reside within a tree structure. What you're seeing here, and this is really kind of what we were bringing to the table, is that you can take, this is by no means high throughput, absolutely not, but it's not zero throughput either. The idea is that you can make various structures, airway structures, where the endpoints are in essence the bronchial chips, the ones I just showed you, that are attached to larger scale three-dimensional 3D printed airways. This is the outside CAD, so actually the airway it would be inside. It's the negative inside. And why is this of interest? Because the minute you recreate airway structures, then you can control the airflows that are going through these multi-generation systems. And by that, you have the hypothesis that you're going to reproduce kind of a faithful journey of an aerosol determined under the laws of physics of how aerosol transport. And that's in essence where initially I came into the field back when I kicked off my PhD many, many years ago now. No further comment on that. So one of the very cool things, and I'm advocating this to the general community, is what I mean for the time being as an in vitro in silico simulation. So on the left-hand side, you really see the system. You can change its gravity orientation, you can play around. So it gives you versatility to recreate scenarios of exposure. Again, not unlike the CFD world, this is by no means a full-scale tree. It covers, you can count yourself, 5 generations, maybe, if you patch things, all the bronchi together, 6, pulling hard. So it's, imagine that you're looking at a single path within a lobe in your lungs and in a specific orientation. But with that, if you do ensemble deposition statistics, here I'm taking a standard case of 2 micron polystyrene beads, 2 micron as Otmar, and that's why I removed even the slide, are perfect candidates in trying to access kind of the deeper lungs, not even between basically the mid to lower bronchi to even the acinar regions. That's kind of that 1 to 10 micron region we discussed. And the physics that we observe, and that's what you're seeing by eye in terms of these deposition heat mats versus what the predictions from computational fluid dynamics are very, very strong. So the point I want to bring in, you have good control of the mechanistic determinants of deposition. Bridging back again to the biology, what we did is we bridged this aerosol exposure system, what I call this multi-generation in situ-like aerosol exposure system, to looking at a proof of concept, specifically looking for one toxic challenge. And here we looked at an apoptotic cascade to really see that we could challenge that bronchial epithelium, where we functionalize the polystyrene beads with a VR1 antibody complex. It's a proxy model, for instance, to environmental exposure, say to something like fly ash. That's essentially what we wanted, but we wanted a specific a response to toxicity, because as we know, everybody, anything potentially is toxic. Polystyrene, by all means, even as you see here in the viability, polystyrene with coated with BSA. So we were able to show that you take a chip, you're going to give a specific inflammatory response, and you do this with the correct, or at least the realistic physical determinants of flow and mechanistic aerosol transport. If you go down one scale, Samuel, could you remind me how much time I have? 6, 7 minutes or so?
Yes, go ahead.
Okay, because I see that the time is running. So now you take ladies and gents, you just take yourself from the bronchial scales and you go as deep as you can, and you're in the acinar worlds. And I told you the no free lunch rule says, to the best of our ability, we haven't made chips that just cross over one order, say 1 order of magnitude, bronchial to alveolar world, where you'd have literally the scales from the millimeter to about 50 microns or so. We can't do that in one go. So what you're seeing here is an example of our kind of the most advanced chip we ever made. This is a physical chip. So at the time, it was purely looking at determinants of aerosol transport. The beauty in this chip, and I guess it's old now, it's over 5 years ago, is that you see this acinar structure. It has very thin walls, about 10, 20 microns surrounding the alveolar tree. It is a planar tree, okay? So it's not a space-filling structure by no means, because photolithography, classical microfluidics just do not permit to have anything that would be realistic alveolar or acinar kind of volumes. It's just not feasible engineering-wise. So these are extruded 2D planes. They are surrounded, what you see on the left-hand side in the exploded view, with water-based channels that are exerting a strain, well, pressure that translates to wall strains that translate into flows. Instead, I always say, instead of me trying to explain this in words, look at the videos, they will give you a sense of what's going on. So what your eyes are not seeing is that when you have just a few % strains of the alveolar walls, the integration of all those little strains, which are physiologically matched. So when you and I breathe here and don't go out running, then we're, in the 5-7% strains. So that's not much motion, but you integrate this on large volumes, you have a huge motion of volume. So conservation of mass, it's telling you, you're going to start sucking in and relaxing these flows. So the flows you see are the analogy of diaphragmatic motions. This is very, very different, and that needs to be understood from, say, mechanically ventilating from the trachea. So this is a much more natural feel. For your eyes, the particles you're seeing have nothing to do with aerosols. They're saturated suspensions for you to see the nature of the motion of the flow that ensues from these wall motions. But you can appreciate that there's weird kind of flow structures going on. I'll just say a short word about this. So on the left-hand side, we invested a lot of time, and I came from this field to understand and quantify what kind of possible alveolar flow structures exist in an acinar tree. There's a range of families of them. The bottom line is, do not ever forget, especially for either toxicity or drug delivery, that half of all the alveoli in our body, forget this chip for a moment, reside in the last 2 generations. And that means that by and large, and this is well known even from histology, most of the deposition of whatever aerosol hits the proximal acinar generations when you're aiming for the acinar world. That's important to keep in mind. And with that, I'll show you something else, but I wanted you to appreciate on the right-hand side, if you take just smoke particles and you're seeing a video in real time, locally, if you had a microscope and you would go, this is kind of the dynamics, potential dynamics you might anticipate locally in an alveolus. It's a funky world. It's a very complex physical world where you have, as Otmar said, diffusion, sedimentation, but now they actually even interact with the local airflows. So they loop around, they can leave, they can exit. It's a very, very non-intuitive world that goes on when you try to predict deposition there. But with that, in vitro and silico can be done. And I'm going to try to help the reader kind of focus. The first rows are everything to do with the experiments. Again, ensemble experiments of multiple hour exposures to various monodispersed particles. Polystyrene, again, being our choice here. And the bottom are computational fluid dynamic simulations for the exact geometry. Now, this is not an acinus. It's just a 2D extruded planar system, as you've seen. And the big picture is that you can get very, very, very strong correlations in the physical predictions. And the key point, and it goes also back to what Otmar said, is that, 2-micron particles, those are monsters in the acinus. They're literally like dropping a bowling ball. Your chips are vertically positioned. So these guinea pigs are positioned vertically. So you see that when you enter from the hot zones where you have most of the deposition, it's extremely challenging to get deep into the acinus. In fact, what your eyes are seeing is that by and large, even when you go into a diffusive world of 100 nanometer, you're still largely bound in the first inhalation, okay? When you bring in fresh bolus of air by what we call the tidal front. It's very, very difficult to bring massively aerosols to regions beyond the tidal front, okay? And that's something that the physics really emphasize. But in vitro, in silico, for physical determinants of deposition are very, very strong. If you're trying to be a whiz and how to design smart inhalation therapy, it's still a massive conundrum. It's super hard to be efficient because we're fighting basically everything that's here to screen. In fact, histology has showed that by and large, when you have acinar deposition, the place it actually hits are the acinar rings at the entrance of the alveoli. And it's interesting because it means that it's not so easy to actually even to get yourself in an alveolar cavity.
Josué, last minutes.
Last minute, perfect. So I'm going to go show you just a bit of biology, which will bridge with Klaus Michael alluded, and this was the study where we bridged this acinar world with an alveolar bronchial epithelium. And I really make the case for these pseudo type 1 like Halvi cells if you're interested in doing basically deposition studies that relate to barrier functionalities. They are tremendous epithelial barrier structures. So they're not surfactant secretin, as far as I understood everything in the literature, but they make tremendous barrier properties. And what we've done here, to give you a sense, is we've bridged kind of doing again a proof of concept of these bacterial-like infections using LPS in this case, and looking at innate immune-like responses through the cytokine assessments, and basically leveraging on top of that macrophage-like cells, which are the THP1 here, that boost this innate response. And what's interesting here, this is directly using nebulized suspensions that are then hooked to these little platforms. I'll finish this, and you're welcome to that. And this fits, I think, well with both all the talks we've seen here, we kind of played around with where is the map. I'm looking at there's a price for everything of complexity to throughput. And this is why if I look at where the flexible membrane microfluidic world resides, the complexity is pushing the boundaries. But I personally do not see the microfluidic world being a high throughput world like the weld plates and the inserts. It's going to reside at some interface in between. And that's a reality we have to live by. Whether or not the microfluidics will become this promised kind of new preclinical in vitro go-to, I hope so, but I'm not sure we're going to stay in the future on the traditional PDMS-driven technology. I think this is just a stepping stone as we move forward. So with that, thank you very much. Apologies if I went over the time. I'm absolutely honored to speak today.
Nice talk, Josie.
Thank you, Klaus-Michael. I will.
Samuel, I guess you have the best overview again on the questions.
Yes, once again, Josué, really great talk. For a sake of time, I will take one question from the audience, so which is the following. So, is the role of substrate stiffness known? With your device, could you tune the stiffness of PDMS and to see how substrate stiffness may affect the epithelium and if it affects barrier function?
So it's a wonderful question. I'll take the liberty to phrase the question differently. All the models that that the audience has seen here, and Klaus-Michael would be able to answer this just as easily as me. The PDMS is only relevant in working on strains. There are no cell functions. There are no cells on the PDMS because think of it as an advanced ALI. Everything's still done on these coated PET membranes. All the cellular activity is revolving around a barrier created around this membrane. So it's the encasing of the system that is at best PDMS. The cells themselves are 2D carpets on membranes as all of us are used to. And that's the good and bad of this story. So it's basically 3 walls out of 4 see nothing of a cellular world. And you can tune this softness of the wall, but as long as you don't have flexible membranes or you don't change the membrane itself and you don't make it yourself, whatever's the encasing above doesn't have direct repercussions on the cellular world. I hope this frames the answer to some degree.
Thank you.
Josué, you will be able to also reply to the questions yourself directly in the Q&A.
Okay.
1 or 2 more, so don't hesitate to do it.
Will do. Thank you. Thank you so much.
We can move now to the next speaker.
Yeah.